Hello everyone, and welcome to the last video in Unit 11.6, which is focusing on the sum of geometric sequences. It makes sense that we're doing this because we already found the sum of arithmetic, and we can't just leave poor geometric out. We have to do it for both of them. So you might remember that when we were doing sums, sometimes you can call that a series instead of a sequence, and we have two types. We have a finite series or a sum, and we also have infinite. For arithmetic, we focused only on finite. However, we are going to focus on both for geometric. So our goal for the first part here is to find the sum of a finite geometric sequence, and that means that you have a set number of terms. And I wish I had a cool story for you, like the Gauss story, how he just came up with this amazing formula. I don't have a cool story for you here, so I'm just going to tell you how to find the sum of any geometric sequence, and it is as follows. The sum of any geometric sequence is the first term times 1 minus the common ratio to the nth power divided by 1 minus the common ratio. So let me just label some things just so we're on the same page. Okay. A sub 1 represents the first term to be added. First term to be added. And again, that does not necessarily mean that n equals 1. It represents that the first term, you could start at 5, you could start at 7, but that is the first term. The R still represents your common ratio, so it's important in all of these problems still to find that at the beginning. N represents the total terms added. So please make sure you have all that copied down. A sub 1 is the first term to be added, N represents the total terms you're adding, and R is still the common ratio. So to show you how to use this sum of the finite series, notice in this first example it is finite because you're going from 1 to 12, so it's definitely not infinite. And so if we're applying this idea that the sum is the output of the first term, and I'm just going to recopy it down here, we need to find all this information. Well, it says here, according to the sequence, that my first term, a sub 1, is 6. So my a sub 1 value is 6. The common ratio isn't outright given to me, but we do have the sequence here. So if you took 18 divided by 6, you would get that the common ratio is 3. If you took 54 divided by 18, the common ratio is still 3. And then n is the total number of terms that we're talking about. So if you counted from 1 to 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you are talking about 12 terms that you're adding up. So if we plugged everything in, your sum to 12 would be the first term of 6 times 1 minus the common ratio of 3 to the 12th power divided by 1 minus 3. And if we simplified this in the calculator, you would get, well, if we simplify it a little bit more, the sum would be 6 times 1 minus 3 to the 12th divided by negative 2. So what I would do again is take 1 minus 3 to the 12th, take that answer, multiply it by 6, then take that answer and divide by negative 2. And if you did that in your calculator correctly, your sum is quite large, 1,594,320. So here is why, again, having this formula is nice. The other way you could do this problem is take the first term, plug it in, take the second term, plug it in, take the third term, plug it in, and just keep adding them all up. I would say that's more of a pain than it's worth. So knowing this formula is quite good. So please check to see if you agree with my answer. And let's go on to infinite sequences, infinite series. So what if the sequence is infinite? So what I want to do is write down the finite formula that we just talked about. A sub 1, 1 minus r to the n over 1 minus r. And let's see if we can use this to apply or find anything out about infinite, because I know that it's a little different because we're going all the way to infinity. But let's see what happens. If you look at this initial value here, this initial function, we can see a couple things from it. The a sub 1 value is usually the term when you plug in 1. So if we plug in a sub 1, that would be 3 times 2 to the 1 minus 1, and 2 to the 0th is really 1, and 1 times 3 gets me 3. So my a sub 1 value is 3, which I saw here. My common ratio, if you remember the formula from finding any geometric, looks like this. Looks like a sub 1 times r to the n minus 1. So any number that's being raised to the power is your common ratio. So our common ratio in this case is 2. And the number of terms we're talking about is infinite. So if we use this idea and plug in to this formula, we'd have that our sum is the first term of 3 times 1 minus 2 to the infinity over 1 minus 2. And so this sum is a little odd because if we take 2 to the infinity power, even if we're subtracting it, this entire top is going to be some kind of infinity. And if I take an infinity divided by negative 1, it may be a negative infinity or positive, but nonetheless, we are not summing to a specific number. So in this example, because our answer is probably going to be infinity, we're going to have no solution because there is no sum, because having a sum of infinity doesn't make sense because we don't know exactly what that is. So if we're going to get a little bit more into eventual calculus lingo, this series diverges. It does not sum up to a specific number, so that's why there is no solution. And I want you to notice, before we go to the next example, that the r value was 2, which is larger than 1, which has something to do with this answer. In the next example, we have infinity again. So let's use the finite definition to see what we can find. The first term, I know from looking at this, is 4. Even if I didn't just know that, if I plugged in 1, 1/2 to the 0th is 1, 1 times 4 is 4. So a sub 1 is 4. The common ratio is what's being raised to a power, so it's 1/2. And so if I want to find the sum, that would be my first term 4 times 1 minus 1/2 to the infinity power over 1 minus 1/2. Now what's interesting this time is last time we did this, 2 to the infinity power is going to infinity no matter what. But if I raise 1/2 to the infinity, that really means 1 to the infinity over 2 to the infinity. 1 to any power is 1. So this becomes 1 over 2 to the infinity. And if you think about limits, when you're taking 1 and dividing by a huge number, you are getting insanely close to 0. So all of this can be replaced by 0, which means that we have 4 times 1 minus 0 over 1 minus 1/2, which is 4 over 1/2, which actually gets me an answer of 8. So interestingly enough, this time the series does converge, which is the opposite of diverge, on the number 8. And what's interesting is my common ratio was not above 1. My common ratio was 1/2. And because I had a fraction here, I was able to use this logic of converging to 0. And so that has something to do with my formula for infinite and also to understand in what situations you can apply it. So if I copy a couple things onto the next page here, we had, in that last example, 4 times 1 minus 0 over 1 minus 1/2 in that final stage. Or if we kept going, we had 4 over 1 minus 1/2. The reason I bring this up is if we look at the previous example, 4 represented my first term, and 1/2 represented my r value. So because this infinite series worked, I wonder if we can get an equation out of what we have left over. If 4 is my first term and r was 1/2, this is how I can find the sum of any infinite geometric series. So if you ever see something like 1 to the infinity power, you can use this formula instead. But unfortunately, this formula only works under certain circumstances. Back here, I noticed that if r was above 1, it didn't work. But if r was a fraction, it did work. So here are some restrictions. So by definition, this idea of an infinite series only works is if my common ratio, the absolute value of my common ratio is less than 1. What that really means is that my common ratio has to be between -1 and 1 in order to work, which we saw back here again, because 1/2 is between, and because we were able to converge to be 0, it ended up working. So this is the restriction we need to keep our eye on. And also, it would make sense to me to say that r cannot be 0, because you'd be saying that the common ratio between two numbers is 0, which doesn't make sense with division. So this is a restriction, and so is this. So let me show you how this would apply to actual examples, but please make sure to have this written down. Find the sum of the following sequence. And so when we want to find the sum, what we're hoping to use is this infinite relationship, because we see the ... But in order to apply this, we need to find our common ratio. Because 3 is the very first thing I see, I know that a sub 1 is 3. To find the common ratio, if we take the second term and divide it by the first term of 3 over 1, that is the same as times the reciprocal. So that is 9/12, which is really 3/4. If I take my third term of 27/16 and divide that by 9/4, that's really 27/16 times 4/9. And remember, you can cross cancel. This goes in here 4 times. This goes in here 3 times. So it looks like I have a 3 on the top and a 4 on the bottom. So we got the same common ratio, which makes me think that my r is 3/4. Now, before we jump right into plugging this in, let's see if we can use it. Is this r value, does it meet these restrictions? Is it between -1 and 1? Yes, it is. So because this works, we can use this idea. So we can say that the sum of this infinite geometric sequence is going to converge specifically at the first term, which is 3, divided by 1 minus the common ratio, which is 3/4. So that would be 3 divided by 1/4, which is really 3 times 4 over 1. So it's going to converge, and the sum is going to be 12. The last example gives you the sequence, but also gives you a formula. And so let me show you two things. Again, we're trying to figure out if we can use that infinite sum. And this can actually be written as, because if 25 is being divided, you're really taking 1/25 times 3 to the n. So that might be interesting to write down, because if I come over here and find my common ratio and take 3/25 divided by 1/25, again, that's the same as 3/25 times 25 over 1. So I get the ratio of 3. And notice that this r is already being raised to the power, so this has to be my common ratio. So we noticed it here and here. So my r is 3. So that gives me pause, because if I would like to use this infinite geometric sequence formula, that should be the sum is the first term divided by 1 minus r. The only way I can use this is if r is between -1 and 1. But because r equals 3, I am not allowed to use this, which means that it does not converge, so the answer would be no solution. Okay, so you can write yourself your note that it is not between 1 and -1, so that means I cannot use this formula. So I know that it diverges, and the answer is no solution. Okay, so keep all these formulas in your mind. We will be practicing this more in class tomorrow. Thank you for your attention throughout this unit, and best of luck on your test. Thanks.